This paper was given to the American Physical Society March Meeting at San Antonio, Texas in 2015. 2 years ago at Baltimore at the APS meeting, I described the structure of icosahedral quasi-crystals. The structure was warmly approved by the attendant membership, and the discussion extended an hour into extra time. Today my topic is more physical. The problem is this: how does a periodic probe, such as an X-ray beam or an electron beam, interact with an aperiodic solid to produce a periodic response in geometric space? I shall begin by refining that term, geometric space, and then on the basis of the structure discuss diffraction and quasi-structure factors before giving you the Log-Lin metric and its use in geometric space. The first problem is mine. You've been told that the diffraction pattern of the quasi-crystals is in Fibonacci sequence. And you know what that sequence is. Each term is the sum of the two preceding terms. The simplest Fibonacci sequence begins with 0 and 1 and is listed on the first column. The Fibonacci sequence has an important property. The ratio between successive terms at high order tends to the golden mean tau. 1.618034 ... It's an irrational number. Elsewhere, the ratios oscillate about tau. These oscillations are not observed in the quasi-crystal diffraction pattern. So let's try a different sequence. We start with 1 and proceed to tau, etc. Now we're getting warmer. The quasi-crystallographers say, look, we have 3 rational indices and 3 irrational indices. We have a 6-dimensional structure, they say. But I don't know what a 6-dimensional structure is, and they don't show it. The trouble is that they're very good at adding and subtracting, but they don't know how to multiply and divide. The ratios are given here on the 4th column. And what you can see is that what we have here is a geometric series. It's firmly 3-dimensional. 3 of their dimensions are redundant. I can illustrate this with a stereogram from the icosahedral structure. I've shown also, these are the axes of the icosahedral structure. And shown also are, for the first time, the diffraction planes. And the indices are all 3-dimensional, geometric, simple, complete. I've indexed every beam in Shechtman's data. I've calculated every structure factor. As Einstein said once in similar circumstances, it doesn't matter, it's right. I first submitted this structure 7 years ago. Well, what is this structure? Here we have an icosahedral cluster made up of icosahedral unit cells. Each unit cell is extremely dense in the proper sense of the word. The density depends on the precise ratio of the diameter of the solute atom at the center to the solvent atoms on the corners. The density, atomic density, is 17% greater than that of the equivalent structure in the face-centered cubic structure. And remember that the matrix phase in melt-spun aluminium-6 manganese is face-centered cubic. So the FCC structure is the nearest approximate to the quasi-crystal structure in 2 senses. The unit cells are edge-sharing, not face-sharing as in crystals. And this has 3 consequences. There's no Bravais lattice. The stoichiometry is 1 to 6. This is because there's a 1 central atom and 12 corner atoms edge-sharing, divide by 2, 1 to 6. Thirdly, the unit cells are edge sharing with multiple edges, and the result is that they're aligned, as you just saw in the model. This alignment is different from the dense tetrahedra infused silica, which are misaligned. And it illustrates the simple fact that quasi-crystals bridge the structures between glasses and crystals. The structure is hierarchic and therefore infinite in extension. It's also uniquely icosahedral. The structure is thoroughly geometric. Each golden rectangle you see has a width to length ratio 1 to tall. Let's work out what is the width of the cluster. 1 over tall plus 1 equals tall. Tall plus 1 equals tall squared. So the stretching factor is 1 to tall squared. And for the supercluster, tall to the 4th. And for the supercluster order 2, tall to the 6th. You've got the idea, haven't you? This is a logarithmically periodic solid with a logarithmic period, tall squared. Let's go on to diffraction. Bragg diffraction in crystals is quite easy. You have a periodic probe, you have a periodic lattice oriented to the Bragg condition, and there's a perfect match. In Bragg diffraction, each line corresponds to one interplanar spacing. Quasi-crystals are more complicated. Pick a plane normal, and it will be obvious to you that each diffracted line is due not to a single spacing periodically repeated as in a crystal, but it's produced by multiple interplanar spacings. In fact, that whole series of spacings that we saw before in the geometric series. What you measure with a quasi-Bragg peak is not an interplanar spacing, but a set of interplanar spacings. When you measure a diffraction angle, you measure not 1D space, but all of them. So let's go on to structure factors. In a crystal, what the structure factor does is to project the locations of each atom in a unit cell onto a selected plane normal, and then add the projections. Let's take two examples from the face-centered cubic structure, the 100 to start with. There are 4 atoms, and the structure factor is 1 plus 1 minus 1 minus 1, 0. This line is forbidden. Let's look at the 200. 1 plus 1 plus 1 plus 1, 4. This line is allowed. This is the way you show that the reciprocal lattice for the FCC, for the face-centered cubic structure, is body-centered cubic. But notice an important point. When we had half integral projections, we had destructive interference. And when we had integral projections, we had constructive interference. Well, what about the quasi-crystal? Think about the interplanar spacings. 1 over tau, 0.6. 1 integral. Tau, 1.6. Tau squared, 2.6. And some more integrals at higher orders. It's therefore not surprising that the structure factors are of order 2. Not 1, not 3, not 4, not 5. 2. 2 lambda equals 2d sine theta. 2's cancel. Every term in Bragg's law is different from every term in the quasi-Bragg law, excepting only the wavelength lambda. The quasi-Bragg law is a new law in physics. The factor 2, that describes the second order diffraction we call the heuristic order. And let's give an example. In the crystal, we have a periodic lattice, so we can calculate the structure factors on the unit cell. But the quasi-crystal is aperiodic. We have to calculate the structure factor on the whole crystal. Well, we can't do that because it's infinite. So we have to approximate and truncate. In this case, to a supercluster order 6 with 100 million atom size. And there are 5 points to notice. Bragg diffraction occurs on track 1 on the left. The structure factor is 0. All structure factors are 0. There is no Bragg diffraction. But when you scan the angle off the Bragg angle, the quasi-Bragg peak pops up. And as a computational fact, it pops up at the same relatively displaced angle in all quasi-Bragg peaks. There's a systematic reason for that. We'll come to it. Fourthly, when you square the structure factors, you calculate the relative intensities and they match experimental values very well indeed. It's confirming evidence. And fourthly, this divergence from the Bragg angle gives you the measured metric. Let's see if we can understand that better. In crystals, CS, the compromised spacing effect, is 1. But in quasi-crystals, we have a periodic probe, as the cosine is, and a geometric lattice. Well, we have to expand that cosine into its power terms in the normal way. And what we find there is, again, this projection. H is geometric, and R is the sum of geometric terms, but you can represent it as a product of several quasi-scattering factors, and then this turns into a geometric term. So it's now obvious what we're doing when we scan the angle away from the Bragg angle. We're finding the maximum match between the periodic probe, described by a cosine, and the geometric crystal, quasi-crystal, described by the geometric term in the cosine expansion. And what is the value of the metric? I give you an intuitive value first, and then simulated value. And the intuitive value is that it's got something to do with the logarithmic periodicity t squared, divided by t squared. And it's got something to do with the heuristic order, half integral. And the intuitive value is 2.5 over tau squared, 2.5 being the nearest half integral to tau squared. The simulated value is easy to find, and the simulated value is 0.947. And this is close to this approximation. And when we use the simulated value, we find consistent values for interatomic spacing, cell size, cluster size, supercluster size, etc., etc. And of course, relative intensities. And this leads me to the first point in my conclusion. The second point is that all measurement on quasi-crystals with periodic waves depends on the Log-Lin metric. It's generic. It includes high-resolution TEM, which does not image atoms. It includes Fourier transform analysis, which is misleading without the Log-Lin metric. Thirdly, it's a matter of definition. The International Union of Crystallography defined crystals as solids with a sharp diffraction pattern. But here we have a structure which is edge-sharing, which has no Bravais lattice, which is aperiodic, which does not obey Bragg's law. It's certainly not a crystal, but it does have a sharp diffraction pattern. And what it means is that it's time to redefine Yakra, but I don't have time to do it. Fourthly, what we have discovered is not 6 phony dimensions with false, mythical guesses. What we've discovered is a new space for physics, geometric space, with a generic metric which is consistent, systematic measurement of interatomic spaces and high-order superclusters and simulated intensities. You can even invert the metric and use geometric probes to investigate periodic structures, including crystals, with new functionality. Well, at this point, the chairman of the session asked the membership for questions. There was a stunned silence. However, I would like to add one retrospective for the purpose of this video presentation about the logarithmically periodic solid. Now that we have a proper diffraction theory, there's a great need to search for defects by dark field phase contrast microscopy. Little work has so far been done for obvious reasons. For example, the late Linus Pauling described a hole in the icosahedral structure. It does not occur in the unit cell or the cluster, but which we previously described as interstitials in the supercluster. Now, the important point is this. Whether the LPS is an ideal quasi-crystal, or whether the quasi-crystal is a defective LPS, are two considerations that are less important than the simple fact that they give us new physics.